Hello, in this lecture I will talk about support vector machines. I will use two sets of slides. This is the first one of those. In this set of slides I will talk about the concept of margin, which is very important for support vector machines. I will define what is a functional margin and what is a geometric margin and how they are related. And then I will talk about the Lagrange method, known as Lagrange multipliers, which is an optimization method that we are going to use for finding the optimal margin. So consider logistic regression, where the probability of y equals 1 given x with parameters theta is modeled by a function h of x, where this h will be the evaluation of another function g of the dot product of the parameter vector and the input vector. So this g we are considering it to be the sigmoid function. Then we can predict a 1 if the input x, when you evaluate that x in the h, you get a value that is at least 0.5. Okay, when you have a 0.5 or larger. This is because of the shape of the logistic or the sigmoid function. And saying this implies that the dot product then is at least 0. Now, consider a positive training example. So the label is 1. The larger this dot product is, the larger also the evaluation of h is going to be, and thus also the higher our degree of confidence that this label is a 1. Thus informally we can think of our prediction as being a very confident one, that y equals 1, that we have a positive example if the dot product is significantly larger than 0. So let's see this in the plot of the sigmoid function. This z here in the x-axis is the dot product of the parameter vector and the input vector. So what we said in the previous slide is that if this value is 0 or larger than 0, so if the z is in this point or to the right of this point, then the output will be larger than 0.5, or at least it will be 0.5 when you have z to be 0. Okay, this point here is 0.5. So what we also said is the larger z is, so as you go to the right, the output is going to be a larger value, and we can say then that with a larger output or larger dot product here, we will feel more confident that our point is really a positive number or a positive example. To the contrary, if we go to the left, starting with some negative number, we start having values less than 0.5. So that would be a label, the prediction of the label will be 0. And as we go more to the left, we are going to be more confident that the output is going to be a label 0. Okay, so this is the function g, this is the sigmoid function. Now we also need to remember that, for example, if our model, this dot product of theta and x, is this line, for example, okay, every point or every input vector that when you compute the dot product you get a 0, is on this line, the separating hyperplane. If the point, like in these examples here, these squares are above the line, then the evaluation will be larger than 0. And if the points are below the line, like these circles here, the evaluation will be less than 0. Okay, so let me go back. That's why we say here, if this value is 0 or larger than 0, the prediction will be to be a 1, and this will be considered to be 1 because we are going to have at least a 0.5 in the sigmoid function. Similarly, we think of logistic regression as making a very confident prediction of y equals 0, so a negative example, if the dot product is significantly smaller than 0. Okay, so again, let me go back. What we're saying here is in the left side, if this product here, this z, is a very large negative number, so we're talking about a number that is more to the left side, then we are more confident that that example is a negative example, so with label 0. So given a training set, again, informally it seems that we have found a good fit to the training data if we can find a set of parameters theta such that this product is significantly larger than 0 whenever the label is 1, and this product is significantly smaller than 0 when the label is 0, so when we have a negative example. Since this would reflect a very confident and correct set of classifications for all the training examples. Okay, so this concept of being significantly larger than 0 or significantly smaller than 0 is what we call a margin. But there are two kinds of margins. First, let's talk about the functional margin. We will consider a linear classifier, again, for a binary classification problem with labels y and features x. In this case, we are going to use as labels the numbers -1 and +1. So the negative examples will be -1, not 0. And instead of the vector theta, we will use the parameters w and b. So our classifier can be written as h of x, where we have parameters w and b, where this w will be the weights that will give an importance to each of the input variables, and this b is going to be our bias parameter or intercept parameter, which will be independent of the input variables. Hence, the evaluation of the function g of z equals 1 if this z is at least 0, and it will be -1 if the z or the evaluation of z is a negative number. So given a training example x, y, we define the functional margin of the parameters w and b with respect to that training example as gamma circumflex equal the product of the label y and the evaluation of the model. So some important points here are: first, this I is not an exponent, it's an index. Okay, so here we're talking about example I, where we have the input X and the output Y. Then the functional margin, or the letter we're going to use for the functional margin, is the gamma with a circumflex. In this case, we're defining the functional margin for one example I, and that margin is simply the product of the label for that example I. And if you remember, labels could be only -1 or +1. And here is just the evaluation of our model of that example I. So if the label is +1, so if we have here 1, then the functional margin to be large, we need the evaluation of the model. So this expression here, we need it to be a large positive number. Okay, because here we have 1. If we want this product to be large, then we need the second factor, this expression, to be a large number. Conversely, if we are talking about a negative example where y equals -1, so if this is a -1, then for the functional margin to be large, we need the evaluation of the model to be a large negative number. So if we have here a -1 times minus something here, we will have as a result a positive number. Minus times minus gives you a positive. And if we want this result to be also large, we need this to be a large negative number. Moreover, if this product is positive, so it is larger than 0, then our prediction on this example is correct. Hence, a large functional margin represents a confident and correct prediction. So this sentence here is very important. If this product is larger than 0, the example is correct. And that is true because consider first a positive example. If this is +1, this evaluation here should be above the model here, or at least on the model. And if this point here is above the line, above our model, then this is going to give you a positive number. So positive times positive, you will get a positive number which is larger than 0. And if we were talking about a negative example, then this is going to be a -1, and the evaluation in the model is going to be below the model, below the line. So we will have, again, in this case, a negative number. So a negative times negative, it's again a positive number. So this functional margin is simply a formula that can tell you if a given example I is correctly classified by the model defined at this moment by the vector of parameters W and the bias B. For a linear classifier with the choice of h of x equals g of the model here, note that if we replace W with 2 times W and B with 2 times B, then instead of evaluating this expression, we will have the evaluation of g of 2 times the product of W and x plus 2 times B. And this would not change the final classification. So what we're saying here is, if we multiply or scale the model, in this case by 2 or by any positive number, we are not changing the final classification, because we are simply generating a number that is closer to 1. Okay, so we don't change the classification. However, what we're doing is we're not changing the classification, because the classification depends on the sign, but we're changing the magnitude of this expression. We are multiplying this expression by 2 in this case. And what we are doing then is scaling the functional margin. So we don't change the final classification, which in this case would be a positive example, but we are changing the margin. So it's like we are moving the point far away from the decision boundary. It seems that by exploiting our freedom to scale W and B, we can make the functional margin arbitrarily large without really changing anything meaningful. So this is a good point, because it means that we can play a bit with this vector of parameters without changing the final classification, and this is something that is going to be useful when we derive the support vector machine algorithm. So just remember this: we can scale the weights. By doing this, we are increasing the size of the margin, but we don't change what it is more important here, which is the final classification of a point. Intuitively, it might therefore make sense to impose some sort of normalization condition. Okay, so it is good that we can scale the vector of parameters, but this could be also misleading at some point. So it is a good idea to normalize this vector of parameters, and in this case we're going to normalize it to be 1. We might replace then W and B with W divided by the norm of W, and the same for B divided by the norm of W. And by doing this, we are normalizing the functional margin. So given a training set S in which we have m examples, m points, we can also define the functional margin for a set of points. In this case, we are going to write it down like just gamma circumflex, and this functional margin for a set of examples will be the smallest margin. So you will consider the margin, the functional margin for every of our endpoints, each one of our endpoints, and you will select the smallest one, and that smallest one is going to be the functional margin for the whole set of points.